Hello, I'm Charlie. This video is about the third paper of my PhD called Supervised Large Neighborhood Search for MIPs. In this paper, we implemented a math heuristic framework for the LNS, and it's a generalized method. So we made very few assumptions about the structure of the problem, other than the presence of binary variables. The LNS math heuristic goes as follows. We start with a while loop, and we initialize some state. On line 4, we define the fixing ratio, which represents how many of the binary variables we're going to fix or delete at this given iteration. Then we pass that information, the state, and the increment to the policy pi. The policy is the LNS heuristic itself. It returns a constraint, gamma, that we pass in to the problem to generate some problem. So the idea is you start with a big problem P, you add some constraint to it to reduce its size, and then you get P prime. P prime should be significantly easier to solve and also gives us a new solution. And then we update the state in the new solution. The main difference of this math heuristic compared to paper 1 and 2 is this while loop. In paper 1 and 2, we only create one neighborhood once at the beginning. To integrate in the LNS math heuristic, we need to define some formalism around LNS heuristics. Here is what a typical heuristic enforces. In this sum, we look into all of the variables that are in the what we call the fixing set M. Every variable in the fixing set will be fixed to its value in the increment, as you can see, where the distance has to be 0 here. A very typical example of an LNS heuristics is rinse. In this heuristic, we fix variables based on the matching set between the relaxation or the continuous relaxation of that variable and the increment. In practice, rinse can work well, but for many problems, it's not good enough. In this paper, we try to develop an LNS heuristic that uses a supervised learning model under the hood. In theory, we can infer the best possible matching set if we have access to an optimal solution. So here we would simply fix all the variables in the increment that are equal to its value in the optimal solution. We can try to predict that optimal solution with a supervised learning model. So instead of x star, we get x bar, which is the predicted value. And we would fix variables accordingly. There's a few issues of doing deterministic selection, as we just proposed. First, the prediction is a noisy estimate of x star, and also it would be the same at every iteration. To address this issue, we propose the following solution of doing stochastic selection. We assign some probability of selection of every variable based on some weight. This weight is calculated based on a matching set between the predicted solution and the increment. So here, if there's a match, we assign the weight MW to that variable. MW is a weight multiplier, and it allows us to tune the distribution. We can analyze this in two different ways. At the limit, if x MW tend towards infinity, we have deterministic selection. Whereas if MW equals 1, then it's a random selection. We'll see a bit later how that affects performance. At that collection, we use the same idea as paper 1 and 2, where during probing, we collect solution from the branch and bound, and sampling is we randomly explore the solution space to create a lot of solutions very quickly. We work with MIPlib, However, this dataset is difficult to work with because it is very heterogeneous. Therefore, we apply a few conditions to filter out the instances that are irrelevant. In the end, from more than 1,000 instances, our test set ended up with 126 instances. In this slide, we compare oracles that have different level of stochasticity. The LNS is perfectly deterministic, and as we go up, the models, I should say the algorithms, are more and more stochastic. We can see that for an error rate of 0, the best performing algorithm is the LNS, as expected. However, if the error rate increases a little bit, then there's a big loss of performance. You can see that there's a sweet spot here where you want to choose a stochastic algorithm with the appropriate level of tuning to get the best performance, the MW that we introduced previously. We also studied different segments of the MIPLib dataset. Here, for example, we have bin packing instances from the MIPLib dataset. We have 8 of them. And here we compare random versus SLNS, our best performing algorithm. We can see that we outperform random only on high sample size and low binary instances. This is intuitive because if we have access to more data, we can make better predictions. However, on most other segments, we do not outperform random, which seems to suggest that this is a very difficult problem to do, to predict high quality solutions on a diverse set of instances. We also experimented with the LAP instances from paper 1. Here, the best performing algorithm is PNF, probe and freeze. This is the algorithm from paper 1. We can see that even the oracle methods from this paper, OLNS and DLNS, do not outperform the heuristic from paper 1. This is because PNF exploits the structure of LAP instances, the SOS1 constraints, whereas the generic methods do not. They only look at binary variables in general. However, they do outperform Gurobi alone. In this paper, we studied an ML-augmented CO framework, a matheristic that allows us to integrate ML predictions to design better LNS heuristics. We saw that weight adjustments in variable selection strategy and additional sampling data can improve performance, and that the strong performance of random LNS suggests that variable selection is a difficult task for generic MIPs. I'll now conclude this video with the last few slides of this presentation, which goes over the future research directions. In this thesis, we explore different specialization versus generalization trade-offs in the landscape of ML or CO enhanced methods. So we have the most specialized paper, which is the second one, where we work explicitly on the network design. And this is the most effective method, in our opinion, because you have a narrow distribution and you can generate instances quite easily. The third paper, we saw that it was quite challenging because we're working with limited data and heterogeneous data. It was the most general one. And then the middle ground is paper 1, where we exploited SOS1 constraints. And this is a sound strategy given that they provide a structuring effect, but they lack broad applicability. Some future research directions. For example, we saw that there is a limited number of real-world instances in practice, so there is a need to develop synthetic data generation techniques that preserve feasibility and boundedness. We need more informative features. We'll be interested to see if we can generate features in a more automatic way rather than doing it via a handcrafted algorithm. There are alignment issues here between the laws, the binary laws that we train, and downstream performance. We could use RL for fine-tuning to help align the model with the downstream performance metrics that we care to optimize for. Labels can be expensive to get. We need near optimal solutions, or at least high quality solutions. We should investigate unsupervised pre-training to get that data more efficiently. There's also a high training cost. We would be interested to look into studying scaling laws for ML's augmented CO and studying more specifically the compute efficient frontier. Finally, I would like to acknowledge my supervisors, Emma Fringer and Jean-François Cordeau, for their guidance and support, Ivado for funding my research, and Canadian National Railway Company, Digital LNS Canada, for the data and the compute resources. Thank you for watching. Bye-bye.